What makes this section on the harder side is actually on the definition of random variable and the difference between random variable and sample space. Okay, what is random variable to start with? Random variable usually denoted by capital X, actually any capital letter except capital Z, as you will see next week. Random variable usually denoted by capital X is a variable with multiple value. Each corresponds to a probability. To occur. Okay, some side note. What is the difference between a random variable and regular variable? Some idea from the past. Suppose, for example, I have 3x plus 5 equals to 7. Now, what is the value of this variable? Then when we solve that, this is 2x equals to 2x equals to 2/3. Okay, now notice that this variable has only one value. Okay, now if you use other value, let's say x equals to 0, then that will be a wrong solution, right? Okay, now here, a random variable may consist of more than one value. Suppose, for example, number of cars, students in Thomas class has. Then the probability that a student have no car at all, let's say 0.6. Probability that a student have one car, exactly one car is 0.35. The probability that a student have two cars is 0.05. Now then we say the random variable x are 0, 1, and 2. Okay, so some students have no car at all, and some other students have only one car, some other students have two cars, and nobody have more than two cars. Let's say this is just an example. Okay, now it means random variable x, which is the number of cars a student in Thomas class have, may be 0, maybe 1, maybe 2. That's the multiple value of random variable. Okay, now then each value of this random variable corresponds to a probability. The probability for a student in Thomas class to have one car is 0.05. The probability that a student in Thomas class has one class is 0.35. The probability that a student in Thomas class has no car is 0.6. Now, that's what it means to say that a random variable is a variable with multiple values. Each corresponds to a probability to occur. Okay. Now, The word random here, is not totally random like in our daily life when we say random as if it's chaos. No, random variable has multiple values. It's not that so many values and we don't know what those are. It's limited. I mean, it's random, but each has probability to occur. Now, where does this random variable usually give us a headache, like confusion? It's usually start with the difference between random variable and sample space. Okay, let's do the following exact example here. Example 1. Okay, suppose we have an experiment of toss a fair coin twice. Now, we have learned from chapter 4, once we know the experiment, once the experiment is given to us, then we would know the sample space, the set of all possible outcomes. The sample space, if you toss a coin twice, will be either head and then head, head, tail, tail, head, or tail, tail. Okay, you can imagine if I toss it once, it's either head or tail. And when I toss it again, for each possible outcome in the first toss, we have 2 possible outcomes for the second toss. Okay, that's how I get this list. Now, for each value, for each outcome in sample space, there's a probability associated to that, right? But no, that's not random variable yet. Okay, for each experiment, automatically we get the sample space, you can say. However, random variable has to be defined after the experiment. What do you mean, Thomas? So let's say, for example, from this experiment, I say let random variable x be the number of tail. Then, what are the possible outcomes for this random variable x? And we see we have head, which means no tail, right? We have head tail and tail head, which means we have only one tail. We have tail, which means we possibly have 2 tails. You see, okay? Now, notice that I said earlier, once you have the experiment, then sample space is something coming to us automatically. However, random variable is something we have to determine after we have the sample space. So sample space and random variable are not necessarily the same. Okay, and random variable usually decided most of the time. I can say for your level it's all the time. Random variable will be decided after we know the experiment, because we need to know the sample space first. And actually, I need to emphasize that, especially for your level, that random variable has to be numerical. So you see the sample space we have here, okay, may not be numerical, right? May not be numerical. However, our random variable has to be numerical. Are you with me? Okay. Now, to go on further, I said earlier that if you have random variable, then that variable has multiple value. As we see here, it has possible value 0 or 1 or 2, and each of them has correspond to a certain probability level. Now, what is the probability? If we look back here, what is the probability we have no tail? Then we look at our sample space. What is the probability we have no tail? Now, because it's equally likely, then the probability of having no tail is only 1/4. While probability to get one tail, x equals to 1, will be one tail. That's 2 out of 4. Then probability to get x equals to the number of tail is 2 will be only 1 out of 4 cases, and they are equally likely. Then the probability will be 1/4. Okay, that's for the random variable and how we apply that. Now, once we get a random variable and its probability, we can develop what we call probability distribution. Now, what is probability distribution? Just like frequency distribution, probability distribution is a table. How do I get 1/4? I assume you're referring to the last one. How do I get this x equals to 2? Probability that x equals to 2 is 1/4. X equals to 2 is 1/4 because when I look at the sample space here, okay, there's only one outcome in the sample space of 4 possible outcomes that we want. Okay, there's only one out of these 4. Okay, that's how I get that 1/4. Yeah, I have to emphasize that each one of these outcome in the sample space happens to be equally likely. Okay, happens to be equally likely means each one of them has the same probability. Okay, that's why then probability of getting 2 tail, which corresponds to tail is 1/4. The probability of getting 1 tail, which corresponds to these 2 events here, that's 2/4. Okay. Now let me go back. Then what is probability distribution? Probability distribution is very similar to frequency distribution, where the first column is the random variable or the outcomes, and the second column is probability. When we have frequency distribution, what do we have here? When we have frequency distribution, we have F here, right? First column is outcome, second column is frequency, okay? Now then for probability distribution, the first column is outcome, the second column is the probability. Okay, that's what we mean by probability distribution. At least at this point, when we say probability distribution, it refers to a table. Okay, now what are the possible outcomes for x? The value for x, either 0 or 1 or 2, each with probability values. Now you will see when I add this When I add these, the total should be, as expected, that should be 4 over 4, which is 1. Okay? Just like frequency distribution, the frequency has to be positive. Now, when it comes to probability, then you see the value here has to be all positive or 0, positive or 0. Okay, cannot be more than 1, cannot be less than 0, and the total has to be 1. Maybe I write it down as a side note. The value here has to be between 0 and 1, and the total has to be 1. Okay, the total has to be 1. Actually, if we look back to this example here, in the previous example, let's call that example 0, then we can create a probability distribution for that too. We can create probability distribution for that. The random variable is x, and the probability will be p. This is x, this is p. The output 0 has probability 0.6. Output 1 has probability 0.35. Output 2 has probability 0.05. Therefore, the total has to be 1. Okay, now that's for a random variable and probability distribution for now. Now, let's do some examples from the book for now. If you have your textbook, please open together with me. Let's say question number 8. Let's say question number 8 on page 210. The question is it a probability distribution? Is the distribution a probability distribution? Okay, let me ask you to work on that. What you need to do is this, though. You look at the table, do you see all the entries are positive between 0 and 1? Okay, you know the things that you need to check the entries on probability column has to be between 0 to 1. And that one you can just visually check that, right? And it is true. But then the second thing you need to also check is that the total probability is equal to 1. Okay, I think that's the one failed to happen. Okay, let me ask you to add them first. Do likewise for number 10. Do likewise for number 10. Okay, number 8. Number 8, the entries are all between 0 to 1, but the total probability is, what is the total probability? The total probability I see here is when I add them, I get 0.977, which is not equals to 1. So it is not, it's not a probability distribution. Okay, so it is not a probability distribution. For number 10, however, when you check, each entry is between 0 to 1. Each entry is between 0 to 1. And the total probability is equal to 1. Which means for number 10, it is a probability distribution. Okay, let's do one more thing. This time I will jump to question number 18. Question number 18 on page 212. You know what? Let me do this. Give me 1 minute. I take the picture so that we can look at that together on the board, on our lecture notes here. But give me a second. Okay, I'm back. Number 18. That's from your textbook 5.2, number 18. When you give a casino $5 for a bet on the pass line in a casino game of dice, I think we usually call that crap, there is a 251 out of 495 probability that you lose $5. And there is 244 out of 495 probability that you make a net gain of $5. So from this question, let's summarize first what's the random variable. Let X be the gain. Now then, this X will be, what are the possible value for X? Either you lose $5, that's -5, the opposite of gain, or you win $5. Okay, those are the possible outcomes. In fact, from the passage from that question, you see probability that we gain -5, that's another way to say lose $5, is 251 over 495. And probability to win $5 is 244 over 495. Now, because there are only two possible outcomes, therefore, when I create the probability distribution, I expect that, let's say this is the probability distribution. This is X, this is P. The outcome of -5 is 251 over 495. And the outcome 5, winning $5 is 244 over 495. Then the total will be, when you add them, you will see the total is 495 over 495, which is 1. So now that's our probability distribution. Okay, now I will go on from this lecture here, from this probability distribution. How do we find the mean and standard deviation? Let's define this first. The expected value of random variable X denoted by capital E, parenthesis, random variable capital X, is given by expected value of X equals to the sum of Px. Is equal to the sum of Px. Now, this expected value is also denoted by, surprisingly, mu subscript x. Now, you can ignore, you can omit that subscript x if the context is clear that we are dealing with only one random variable. Okay, you can omit that, but usually in case of random variable, we keep writing the random variable notation as a subscript. If you use mu, and if you use that E expectation notation, capital E parenthesis capital X, that's the expectation notation. Now, the reason this is also called mu of X is because expected value of this random variable is also, you will see, is the average. This is the mean of this random variable X if the experiment is done or is performed many times. Okay. In other words, later on when we compute the expected value here, later on, the result will give us the average winning or losing if negative if we play this game many times. Okay, the expected value of winning or losing on each game if we play this game many times. Now, furthermore, we have seen this notation in the past, the sigma notation in the past. Okay, and I hope you still remember how to use it. Okay, the expected value or the mean of that random variable is equal to the sum of px. The sum of px must be doing the extension here, px, and the sum that we are looking for is the one underneath here. So I will do what we call the first extension. I will do first extension. I hope you remember that. And I multiply the p and the x here. In the past, we used fx. Right now, it's px. Okay, so this will be negative 1,251 over 495. I multiply the numerator. And the bottom one here will be 1,220 over 495. If I add them, I will get negative 31 over 495. Which, if I use my calculator, 31 divided by 495 is equal to negative 0.06263. Okay, now what is the interpretation? What is the interpretation? The interpretation is if we play this game many times, then we will lose $0.06263 on each game on average. Okay, that's what we have for expected value. Just to remind us, in the past, let me see, somebody sent me a message. Oh yeah, thank you. So thanks for the correction. It should be negative 1,255 here. So I need to make correction here. This is, oops, that's negative 35. And therefore, I don't think this is a correct number anymore. 35 over 495 is 0. Oh, that's worse, huh? That's negative 0.07071. Okay, so if we play this game many times, then we expect to lose on average each game 0.07071. Okay, approximately 7 cents every time you play. Okay, now I don't think that's a lot on average, right? I don't think that's a lot. The problem is because we think we don't lose a lot on average, then we tend to play long time. Okay, so if you play 100 times, you expect to lose $7, which is not really a big deal as for you maybe. However, if you have a casino and you play these games and you have 1,000 people playing these games, and each one of them play 100 times, then casino will make $7,000 from this 100 people, from this 1,000 people. Okay, that's why casino is actually a very good business that make Las Vegas survive. Now that's for the expected value. Now the variance of random variable x, I just continue right away. The variance of random variable x denoted by var x or sigma squared parentheses x or sigma squared subscript x is given by the variance of random variable x is given by the sum of px squared minus the square of the sum of px. Okay, that's the variance. If the context is clear, then you may want to just drop this x here, the subscript. But if you write using this style, you should include the parenthesis x. Okay, yeah. Only when you write it using this style, this subscript here, then you can omit the x. But once you write using these two notation here, you need to use that parenthesis capital X, just like the expectation. Okay, just like the expectation. We don't write expectation notation by just capital E. No, you can't. Okay, if you really don't want to write the random variable, then use mu. Okay, but if you use capital E, you need to include the parentheses capital X for the expectation of X. Now, let's look back a little bit to what we have done in the past. If you remember the formula, we say that mu equals to the sum of fx over n, right? That's what we learned before. Now, imagine if we change this into the version of probability distribution, then the position for f now becomes, look at the probability distribution. Frequency distribution becomes probability distribution. So when you have frequency distribution, we have this. This is x, this is f, right? Okay. Now, right now, when we have probability distribution, we change the f becomes p. Okay, we change the f becomes p. Right? We change the f becomes p. Now, at the same time, the n is the value you have down here, right? Now, what is the value you have down here now? One. The total probability has to be 1. So if you memorize the formula we have from the past, if you memorize this formula here, then it will be quite easy to remember the current formula, because you basically change the F becomes P, and the capital N now becomes the total probability 1. Okay? Now, furthermore, if you remember the formula for variance, when we have frequency distribution, that's the capital N sum of fx squared minus the sum of fx being squared over n squared. That's what we have from frequency distribution. Now you change the f becomes p, and the n becomes 1. See what happened. If n becomes 1, I will get 1 times sum of f becomes p, px squared minus the quantity of sum of px being squared over 1. But without that 1, though, I mean, if you omit the 1 here, I mean, divided by 1, multiplied by 1, then the formula here is basically the formula we have here in the blue box. You see what I mean? Okay, so I hope you still remember that variance formula. Now you do that little modification. Okay. One of the reasons why I emphasize that you need to memorize the variance formula in the second week is because of, one of the reasons is because you need to see the relation right now. Okay, let's do example 1. In our example 1 that we have earlier, in the experiment of tossing a fair point twice, the experiment toss a coin twice, a fair coin twice. And let the random variable x be the number of tails occurred. Then we get x are, the possible values for x are 0 and 1 and 2. We get the probability distribution earlier. You can just look back. We get the probability distribution earlier to be, let's say this is x and p. This is x, this is p, 0, 1, 2, with probability of 1/4 here, 2/4 here, and then 1/4 here, whose total is 1. The total is 1. Now, then find the expected value of x. So if you toss a fair coin twice, many times, on average, how many tails you get? Then for us to find it, we need to find the sum of px. So I still need you to remember how to read the summation notation. Basically, then we do the first extension, px, you multiply here, 0 times 1/4 is 0, 1 times 2/4 is 2/4, 2 times 1/4 is 2/4, When I add them, I get 4 over 4, which is 1. Okay, so the expected value is 1. In other words, if I do this experiment many times, toss a fair coin twice, but I do this many times, then on average, I will get one tail. Okay. So sometimes I get, let's say I've tossed it I toss it twice one time, I get 0 tail, and then another one time I get 1 tail, and then another one time I get 1 tail, another one time I get 0 tail, and then another one time I get 2 tails, and then another one time I get 1 tail, and then another 0 tail, and then 1 tail, and then 2 tail, and so on and so forth. Now, if you take the average of these values, as long as you do it long, many times, when you take the average of this value, you expect that to be, that number to be very close to 1. Okay, so theoretically, we say that the expected value will be 1. Okay, that's what it means. Now, how to find the variance then? How to find the variance then? I do the second extension. The second extension will be, if you remember from the first 2 weeks, we will have x squared here, and then px squared. Instead of fx squared, we do px squared. Now, x squared will be 0, 1, 4. Okay, coming from this x, this column x here, coming from this column x, you square the 0, you square the 1, you square the 2. That's how you get that 0, 1, 0, 1, 4. Now then, when you get the x squares, you multiply each x squared by the corresponding probability. Now, if you have your microphone, you can activate that. Help me here. What is the px squared for the first row? What's that there? That's 0, that's right. Okay, how about the second row? The second row is 2, 4 times 1, that's 2, 4. And then the last row, 1, 4 times 4, that's 4 over 4. Okay, now I don't reduce them right away because I know I will add them later. So let's just keep them in common denominator 4. Okay, let them keep common denominator 4. So when I add them, I will get 6 over 4, which is 1.5. That's when I make it decimal. And therefore, the variance will be, the variance of this random variable will be the sum of px squared, in this case is 1.5, minus the square of the sum of px. That is 1.5 minus 1 squared. That's 0.5. That's the variance. Now, once we know the variance, then we will be able to know the standard deviation. Okay, the standard deviation of random variable x, denoted by sigma parenthesis x or sigma subscript x, but not SDX, at least not in my class. No, this is not one of the accepted value for standard deviation for random variable x, at least not in my class. I know some teachers use that, that's totally fine. Some textbook actually do that, that's totally fine. Okay, but in my class, please don't do so. Okay, yeah, we never use the notation SD for standard deviation in the past. That's why I don't allow that right now. Okay, that's why I don't allow that right now. And the standard deviation as expected, that's equals to the square root of the variance. Okay, the square root of variance, I think that's 0. See, that's 0.707 something. One. For B, how did I know that the sum of px being squared is 1? Oh, because of this. What we have here is actually this thing, right? That's the same. Okay, yeah, that's why I get 1 being squared. You see what I mean? Now that's for example 1. Let's do one more example here. Let's do one more example from the book, and then I go on with my example. Example 2, let's say we take a look on which question here? Maybe number 19. Let me ask you to start looking at number 19. While I try to quote it here. This is for number 19. The CNA insurance company tried to insure a 21 years old male, and the premium is, let me try to make it a bit smaller. Okay, and the premium is $250 per year for 100,000 life insurance policy. Okay, so let X be the payout. Okay, now the payout is either payout by the insurance company. Let me emphasize that, by the insurance company. Now, in this case, this male, this 21-year-old male, has 0.9985 probability of living for a year, which means this male this guy will lose $250. Okay, now, however, if he pass away within this next 1 year, then his estate, of course not him, he died, right? Then his estate will get 100,000 together with what he paid earlier minus $250. Another way to say it, then either he loses $250 if he survived this next 1 year, or his estate together with him who paid $250 in advance will get $99,750. Okay, now those are the possible outcomes, aka the random variable. Now, using that, let's construct the probability distribution. Let me make it big this time because the number is quite big. This is the x, which is negative 250 and $99,750. The probability that he survived the next 1 year, living for 1 year, is 0.9985. So my question to you is, can you find what is the probability that he pass away in the next one year? That's right. That's 0.0015. Now, you may wonder, Thomas, how do you get that? Well, we know that's the case because the total probability has to be 1. Okay? The total probability has to be 1. So if we know part of the probability distribution, keep in mind this is always 1. Now, then you use this 1 minus whatever probability we already have to answer this question here. Moving forward, question part B is to find the expected value. Question part B is to find the expected value. Now, let me give you 1 or 2 minutes to compute the expected value. Okay, let me start. Probability multiplied by the outcome here, negative 250 times 0.9985. I get negative 249.625. While 99750 times 0.0015, I get 149.625, which when I add, I get negative 100. Okay, so the expected value is negative $100. So if you have many people, many 21-year-old male buying this policy, then on average, each one of them will lose $100, because it is possible that some of these 21-year-old not surviving the next 1 year, right? So they get the payout. So, but on average, then they will lose $100 per 21-year-old male. Now, to say another way, from the point of view of the insurance company, then it means the insurance company is expecting to get profit $100 per insuree. Okay, to get $100 per insuree. Now, there's a question coming from one of you. Why don't we do the x squared and px squared? Well, so far that's not the question yet. In fact, if we look at this problem set here, they don't ask anything about variance. I will do that later, but let's see part C first. What would be the cost of insurance policy if the company just breaks even instead of making profit? So here's what happened in part B. This is the expected value for an insuree. I think I should say the insured person. Okay. So for the company, for the insurance company, they expect to profit to make $100 from each person they insure. From each 21-year-old male. Okay, so that's for part B. Now, part C, the question is, that's how much they expect to make. In part B, this is how much they expect to make for each person they insure, right? Now, suppose they don't want to do business, they just want to do charity, okay? They say, you know what, I waive my profit, okay? I just want to volunteer my time to do this insurance, so I don't expect to make any money. Then how much the insurance policy is supposed to cost? Well, notice that if you pay $250, they make $100 profit. Okay, now then how much do you need to pay so that they don't get any profit? So the cost without profit will be that $250 that each one of them pay minus the expected value of profit for that $250. So if you change the cost, instead of $250, you make it $150, then the company is expected to make no money. Okay? Then the company is expected to make no money. Now, what I'm about to say right now is a bit controversial, but from here we learn something. An insurance company, just like other companies, is in business for profit. They are not doing charity, they are not doing volunteer work. Okay? Doing business comes with risk, and even without making profit, they still have risk that they need to manage. And of course, asking the company not to make any profit while need to work hard, spend time, spend resources, spend effort, spend emotional energy. It's basically not feasible, right? We cannot expect too much from a business. I mean, they are there for business. Of course, the first thing they have in their mind is like how to make money. Okay, yeah, we expect them not to kind of like rip off, of course, but asking them not to make money is also unreasonable. Okay, so in other words, with this situation here, we don't expect them to charge only $150 though. Okay, that's if they don't make any money at all, but they still need to pay for their employee, they still need to pay for their insurance, they need to pay for this and that. Not to say that if they get a lawsuit, right? Okay, so I don't think anybody if they are in this situation, uh, I don't think any company will just charge you $150. No, you may say, but Thomas, from each person they make $100 though. Okay, so if they have 10,000, if they have 10,000 people to insure, they already make $1 million. Well, don't forget, uh, for each person they deal with, they have some effort that they need to do, right? So dealing with 10,000 people equivalent to 10,000 times that kind of hassle. Okay, so it may be a lot, of course, but come on, for a company to have 10,000 21-year-old males buying insurance from them, you need to give them what you call that, the benefit of gaining such kind of trust. Okay, yeah. Just ask yourself back. You know what? Is it reasonable for you? If yes, then you buy it. If no, then find another insurance company. Okay, but telling them to change their system is just like, dude, you are not the owner, but why you talk too much? I'm teaching you how to be a company, not only how to be somebody being insured. Okay, you need to see from both sides of the game. Okay, we expect more insurance company available such that the market actually running and able to compete, and that way then we have more options as customers, right? Okay, but at the same time we want the business to do good money too. uh, Basically we have more and more options to choose from. Part D, given the expected value is negative from part B, why should a 21-year-old male or anyone else purchase life insurance? The purpose of life insurance is not to make money for you. The purpose of life insurance is what we call risk management. It's not about how much money I make or lose in this policy. It's about what happens if I pass away. Okay, uh, how much I'm willing to pay to mitigate the loss of income for my family if I pass away. Okay, now in this case, then we ask ourselves, am I willing to pay $250 such that in case I pass away, my estate or my heirs, the person who get the money, will get $100,000 to replace my income, the loss of income, to replace the loss of income due to my passing. Okay, so that's more about what question that we're supposed to answer. So of course, when we do, if you look at this as a source of income, you better be the insurance company instead of being the one being insured. If you see this as a source of income, okay, but not everybody should be insurance company, right? Okay, life needs to go on. Somebody still need to do something else, and therefore, uh, if I were this 21-year-old male, I will ask myself, you know what? If I pass away, how much my family need to replace the loss of income due my passing? How long do they need to adjust to that loss? And therefore, knowing how much they need. Let's say, for example, in my situation, my personal situation, I have a wife and I have 2 kids, right? In case I pass away, I asked my wife, hey, you know what? How long do you think you need to adjust to a new life and start working? So between I pass away until she start working, have a stable income to provide for my 2 children and her herself, the answer is, oh, approximately 2 or 3 years, Thomas. Then I compute how much she will need for 2 or 3 years. Let's say she will need $400,000. Okay, so using that as a number, then I will buy a policy that will cover her, my family, in case of my passing, that they will get $400,000 if I pass away. I hope you see my point of view. Okay, so now right now you are not making a big income yet, even if you work part-time. So do you need life insurance? You may need just to cover for whatever expense needed in case of your passing. At least think that way. Okay, but once you make money later on, especially if you are the breadwinner, please think about your family. And this is the point of me picking this question. Okay, the purpose of insurance is not for income. That's a risk management. How to mitigate the loss of income for my family in case of my passing. Okay, of course we are not expecting the policy to pay for my wife and my children's loss of income for the next 20 years. That's too much. That's too much. Okay, something happened, but I need them to also move on, right? Okay, and at one point, my wife and my children have to have their own source of income. Okay, that's how I will explain this insurance. Now, that's the easy part. Let's go on to harder part. What is the harder part, Thomas? The following. Oh, you know what? I forgot something. Let's go back. Earlier, I said that in case you need to compute the variance, then what do? Yes, if you want to compute the variance and standard deviation, then you do the x squared and then px squared. Yeah, if you need to find the variance and standard deviation, then you do this extension here. Okay, you can do it yourself. And from there, you compute the variance. Okay, it happens that in this question, they don't ask the variance, they don't ask the standard deviation. Okay, but to answer our friend question earlier, to find expected value, do we need to find the expected value Do we need to extend the table to x squared and px squared? The answer is no. Expected value is the same to the mean, and that has something to do with the first extension only. Okay, only for the first extension. If we want to find the variance, then we need to do the second extension. I hope that answers whose question earlier? Judy's question. Okay, so no, we don't need x squared and px squared to find expected value. We will need that for variance. Good question though. Yeah, good question. Now, the harder part. I will now use this for the type of question I may ask in my test. Let's consider the following situation. Let a group of people, a group of let's say, yeah, people consists of let's say 6 females. Let me use the word girl instead, and 4 boys. Maybe instead of people, a group of children. A group of children consists of 6 girls and 4 boys. Now then, triplet is going to be selected. A group of 3 children. First one, construct the probability distribution. Construct the probability distribution. Yeah, basically the probability distribution for, I'm sorry, I forgot to say that. For the number of boys selected. And then after that, find the expected value and third, find the standard deviation. Okay, I will start part A. Let X be the number of boys selected. Find, let X be the number of boys selected. What are the possible values for X? How many boys possibly selected? Is it possible that when we select 3 people, well, that's what the word triplets means, right? If we need to select 3 children from these 10 children, okay, so how many boys possibly selected? Is it possible that of those 3 children, none of them boy? Yes, that's possible if all 3 are girls, right? Okay. Is it possible to have 1 boy? Yes, that's possible. Is it possible to have 2 boys? Yeah, 2 boys and 1 girl, right? Okay. Is it possible to have 3 boys? Yes, that's possible. Is it possible to have 4 boys? No, we cannot have 4 boys. The reason is we only select 3 children, right? It's a triplet. Okay, so you cannot select 3 people and you end up with 4. So let me put a notation there. We only select 3 children from these 10. Okay, so we can, of course, it is impossible for us to have 4 boys when you only select 3 of them. Okay, now then, before I put them into probability distribution, let's compute first the probability for each possible, each outcome there. So first I need to compute probability that I get no boy. Probability that we get no boys. We have girls, we have boys. Okay, there are 6 girls and 4 boys. To get no boys, to get no boy means I need to select nothing from here. And therefore, 3 from girls. So this is equal to 6 choose 3 times 4 choose 0 over 10 choose 3. Okay, what is 6 choose 3? Is I know that's 20. 4 choose 0 for sure is 1 over what is 10 choose 3? 10 choose 3, let me work it out here. That's 1. This is 4, this is 3. So that's 120. Okay, so 6 choose 3 is 20, 10 choose 3 is 120. Let me leave it like that for now. Now then, using the same idea, find out what is the probability that x equals to 1. Using the same setup, 6 girls, 4 boys, I need 1 boy because x is the number of boys, right? If x equals to 1, then how many girls? 2. Okay, why? Because we select 3 people. If one of them boy, then the other 2 should not be boy, right? In this case, must be girl. So, and what is the probability? Then that will be 6 choose 2 times 4 choose 1 over 10 choose 3. Using your calculator, or if you happen to know, well, we know the denominator will be 120. Okay, the numerator, there will be 6 times 5 over 2, that's 15, 4 choose 1 is 4, so this is 6 over 120. I will not reduce that for now. Okay, for now, I just leave it like that. I will reduce that later. Okay, I will reduce that later. When I reduce that, I will reduce to the point that they still keep common denominator. When x equals to 2, when x equals to 3, okay, you do it, I do it too. Okay, you try to do it on your own. Try to do it on your own. This will be 1 times 4 choose 2 over 10 equals 3. That's equals to 6 times 4 times 3 divided by 6 over 110. That's 36 over 110. Now, they are all having common denominator 120. If you want to keep them with the common denominator 120, you are totally fine. I strongly do not want you to convert this to decimal, at least not now. Leave it in fractions, okay? Now, if you want to reduce the fraction, try to reduce them to common denominator. What I see here, the numerator are all reducible by 4. So let me reduce the fraction by 4. So 1 over 30 here. This is 9 over 30. This is 15 over 30. And this is 5 over 30. Therefore, my probability distribution is now this is the x, this is the p. When x equals to 0, the probability is 5 over 30. The outcome is 1. The probability is 15 over 30. The outcome is 2 boys will be 9 over 30. 3 boys, that's 1 over 30. Such that when I add them, just to check that you did everything correctly, to check that you do everything correctly, you add these numbers. Okay, you should get 30 over 30 because the total probability is supposed to be 1. Okay, that's for the probability distribution. Now I'm about to give you a break together with some exercise. I want you to do that part B and part C. I will give you 10 minutes together with a break 10 minutes, okay, to answer this part B and part C. Okay, apply the formula we have. Apply the formula we have here. Very similar, very similar to what we did before. Let me show you what I have in mind. So basically, I want you to extend this table. I want you to extend this table. I want you to extend this table with x, px, and then x squared, and then px squared. Do all of them using calculator. I mean, using fraction, I mean. Just do them by fraction. Okay. You will use calculator toward the end. Now, the reason it is easier to deal with them with fractions, because when you multiply by a fraction, you just multiply by the denominator, at least for now. So here this will be 0 over 30, 15 over 30, 18 over 30, 3 over 30. You see what I mean? Okay. Then the total there will give us the expected value, and so on and so forth. Okay, so let me ask you to continue. You need to compute that, complete that table first. to answer the question for expected value and to answer the question for variance of random variable x. We will come back at 11 o'clock. So this will be 0, 1, 4, 9 multiplied by the probability. This will be 0 here. This is 15 over 30, 36 over 30, 9 over 30, which when I add, let me add this first. This is 36 over 30, that's 1.2. And this guy here, when I add 45, 60 over 30, that's 2. Now then the expected value will be 1.2, comes from here. And the variance will be 2 minus 1.2 squared. The 2 comes from here. The 1.2 comes from here. Okay, just like before, the variance of random variable, and every time we talk about variance, it has to be a positive number. 0.56. Therefore, therefore the standard deviation will be, the square root of that. Standard deviation will be square root of 0.56, which is 0.74, 0.74833. Okay, now this is for constructing the probability distribution given this type of harder question. Okay, that's for 5.2. Let's go on to 5.3, binomial distribution.
Professor, I have a question. How did you get 36 out of 30 if 18 times 4 is equal to 72 out of 30?
Is it right? I did it wrong. Hold on. Which one?
We're on row 2.
Row number 2.
You got 36 out of 30, but p times x squared, isn't it 18 times 4?
Oh, no. You were looking at px.
Px.
Now you're supposed to be having p times x squared. Supposed to be p times x squared. So it should be this one times this one. Okay. Mm-hmm. Let me erase the marking here. Okay, 5.3 on binomial distribution. Now, what is binomial distribution? Let's take a look first on the rules for binomial distribution. Now, in application of statistic probability especially, there are some distribution that appears quite often, and binomial distribution is actually one of them. Okay, Now, before we really go into what is binomial distribution and the examples of binomial distribution, let's see first what are the things. How do we know that an experiment, a random variable, satisfy binomial distribution rules? Now, I quote this from our textbook. Give me a second. I copy paste that. A binomial probability distribution results from a procedure that meets all the following requirements. So let's say I write here, let X be binomially distributed. Now, what does it mean to say that random variable X is binomially distributed? Now, that's if, first, the procedure has a fixed number of trials. We usually call that number of trials lowercase n. Second, the trials must be independent, which means the outcome for any trial does not affect the outcome of other trial. Maybe I write it down here. For example, if I toss a coin, let's say 5 times. Okay, so when you toss a coin 5 times, the number of trials is fixed 5. Now, the trial must be independent. When you toss a coin, the outcomes either tail or head. The outcomes are either head or tail. Okay. Now the thing is, knowing if I toss a coin and the outcome is tail right now, it doesn't tell me anything about what will happen in the next toss. Okay, the probability of getting tail will be the same throughout the experiment. Probability of getting head will also be the same throughout the experiment, regardless what the outcome in the previous trial. The third, each trial must have all outcomes classified into 2 categories. Now, we usually call them success or failure. Okay, now, but of course, that's not the only way to look at that. We can also say that, oh, beside success or failure, it is possible it's about tail or head in our, just like in our experiment below. Or it may be boy or girl, or open close, or yes or no, or let's say blue or not blue. Okay, anything that may be that only have 2 categories, and throughout that experiment you have 2 same categories. Okay, now probability of success remain the same in all trial. Probability of success remain the same in all trial. Now this probability of success is denoted by lowercase p. Now let's say in our experiment here, probability of tail is equals to 0.6. Therefore, the p Therefore, the P later on, if we want to see how many tails, the probability of how many tails, the P will be 0.6. Now, I want to add more into this probability distribution. And I think almost all explanation I see for online, missing the fifth one. The fifth part is like we are interested in number of successes only, regardless the order. Okay, now let's look at this example here. Let's say we toss a coin 5 times. Probability of tail is 0.6. So we now have this parameter. Okay, now then how do I write the notation? Notation. If x is binomially distributed, we will write it x wave b and p. So in our case above, let x be the number of tail appearing. B will be, x is binomially distributed with n equals to 5, p is 0.6. Now, our textbook does not emphasize on notation. In my opinion, it would be nice if we emphasize on notation. Therefore, later on, we don't really need to deal with the word problems. We just see the pattern. Okay, x is binomially distributed with 5 trials. Probability of each success is 0.6. Now, let's say, for example, the question is, then find the probability that there are, let's say, 3 tails. So you toss this coin. Apparently, that's not a fair coin. We toss this coin 5 times. Probability of each tail is 0.6. Find the probability that you get 3 tails. Find the probability to get 3 tails. Now, I will teach you how to use calculator. I will teach you how to use calculator. But the explanation on how to do the manual computation, watch the lecture video. In my test, however, you will use calculator. I assume you use TI-84. Okay. Now, when we answer this question, I want you to first write the notation for calculator. So first, this is calculator notation. The calculator notation. You need to write that down. That will be Binomcdf 5 0.63. Now, if we are computing the probability of a certain number of a binomial distribution, then we will use Binomcdf. Okay, and then parenthesis consists of 3 numbers. The first number is the n. The second number is the p. And the third number is the number of desired outcomes, the number of successes. Okay, now then, how to punch this into your calculator? Let's have a calculator view. This is my calculator view. I used that earlier. Now, how to find that Binomcdf? To find Binomcdf, please follow me with your calculator. To find that Binomcdf, you will do things here. There's something called distr here. And for us to get it, I need to press second farce. That's how I get that distribution. Okay. Do you see this farce? You need the distribution, the second. So that's why I press second first and then farce. Then you will get this list. Now, scroll it down, scroll it down, scroll it down, scroll it down. Then you will have Binomcdf here. Okay. Now I will press enter. Then my screen will go to this Binomcdf. Now, how many trials in this question? 5. And then scroll down. What is the P? 0.6. What about the X value? The number of successes we want is 3. Enter. And then you paste it. Boom. So you will see if I scroll it to the left, that's the notation we wrote earlier. That's Binomcdf 5, 0.6, comma 3 close parentheses. And then you press enter. You get 0.3456. You'll get 0.3456. So I go back to my notes. Then I write here, this is equal to 0.3456. Now, once you're done with that, let's do one more problem. A similar problem. What is the probability that B is equal, that the number of tails, P probability that the number of tails is, let's say 1. I want you to write the calculator notation first, and then use your calculator to compute that. I give you 1 minute. Make sure you write the notation first though, okay? Always. Binomcdf 5 for the number of trials, 0.6 for the probability of getting a tail, and 1, the probability to get only 1 tail, which means the other 4 are not tails, okay? Then when I use my calculator, let me shift the view to my calculator. Then I will do second farce and then scroll down. Binomcdf, the number of trials is already 5. The probability of each tail is 0.6. And the X value, the number of successes I want, is now changed to 1. And then enter, paste it, and then I enter again. I get 0.0768. 0.0768. So I get 0.0768. Let's go on further. What if I ask something else? Let's say probability that X is at most 3. instead. Now, to say probability of x is at most 3, then we will basically need to add probability that x equals to 0, probability that x equals to 1, plus probability of x equals to 2, plus probability that x equals to 3. That's what it actually means. Now, notice that we have 5 trials. We have 5 trials. Therefore, we should have 6 possible outcomes. We should have 6 possible outcomes. Sorry with my boxes, they look so ugly here. Those possible outcomes are 0, 1, 2, 3, 4, 5. Okay, now when we say at most 3 successes, we are talking about this effect here. What is the probability that at most 3 tails? And I suppose to add this probability at these probabilities. But since we use calculator, we will not do Binomcdf. I will use Binomcdf. I will use Binomcdf. Where the C actually stands for cumulative. The C there actually stands for cumulative. Yeah, the same understanding with the regular word cumulative we know. When we say cumulative is up to, okay? So probability up to 3. Binomcdf, the notation is actually the same to what we learned before. The first number is the N, the second number is the P, and the third number is the cumulative, up to. Okay, so maybe I'll use a better color here to emphasize. It's cumulative, up to 3. Okay, now the position of Binomcdf is right below Binomcdf on your calculator. Now, let me ask you to take a look on your calculator and try to punch that in. Binom. So go to distribution, scroll down. It is right below Binomcdf. The number of trials is 5. The probability of each tail is 0.6. The cumulative value 1, 2, up to 3. And then enter, enter, enter. 0.66304. That's 0.66304. Okay.
I have a question. How would you get the 0.5, 0.6 when in the notations?
Where did I get the 0.6 in the notation?
Yes.
You mean why 0.6?
Yes.
Well, because in our original question, we know that the probability of each tail is 0.6. That's our P.
But how did you get that P?
Oh, it's just given.
Oh, okay, okay.
Yeah, it's just given. Yeah, it's just given.
Okay, thank you.
Okay. Now then, how about let's say you try this probability that x is, let's say, at most 4. You write the calculator notation first, and then write the result from your calculator. That will be Binomcdf 5, 0.6, 4, which is equal to, somebody say 0.9224. 0.9224. Can anybody else confirm that?
It's correct.
Yes, I have 2 people together with you, then we have 3 people saying the same thing. Okay, then I don't check that anymore. Okay, now let me give you one new example so that we don't get bored with only one example. Let's say, for example, this time, should I call that example 2 maybe? Okay, let x be binomially distributed with n equals to 10 and p equals to 4. Okay, now please don't think this way for now. Please don't think this way. Thomas, I will never do this in my life anyway. Trust me, you will. Okay, trust me, you will. Binomial distribution is one of the second most common distribution we encounter in our life. Okay, now the fact that people say, no, I will never deal with binomial distribution, that's because they never learn binomial distribution, then they never realize that they actually apply binomial distribution in that particular case. Okay, but the application is so far reaching that I cannot believe that you can find a field that never deal with binomial distribution. Okay, now, but for now, we learn the theoretical, we learn the notation. Later on, we apply to the application. You know, so let's say part A, I would like to know the probability that x equals to 7. Part B, probability that x equals to 4. Part C, probability that x is less than equals to maybe 3. And then part D, I do some modification here, probability that x is less than, let's say, 6. Now, but less than 6 means it's only up to, if I have 11 possible outcomes from 0, 1, 2, up to 5, 6, 7, all the way to 10 number of successes. When I say less than 6, it means it's only up to 5. Okay, so without equal sign, strictly less than 6 is the same to say less than or equals to 5. Okay, so that's something you need to do adjustment on. And then once you're done with that, I would like you to do probability that x is less than, let's say, 9. Okay, let me give you 1, 2, 3, 4, 5 minutes for this. Okay, so part A, P equals to binom, because it's only equal to a certain number, then it will be Binomcdf. The first number is 10, the second number is 0.4, and the third number is 7. Let me use my calculator. 10, comma, 0.4, comma, 7. That will be 0.042467. If I want that to be equals to 4, then probability that they are the number of successes is 4 is binom PDF and 0.44, which is 0.25082. Now, probability that X is at most 3, because it's at most 3 means it is up to 3. That's binom CDF N P R, the number of outcomes, the cumulative outcomes. That will be binom CDF 10.43. I get 0.38228. Now part D. Probability that X is less than 6, which means up at most 5. That's binom CDF and 0.45. I get 0.83376. Probability that X is less than 9. The number of successes is less than 9. I need to do adjustment first. Probability that X is at most what? 8, right? And that's binom CDF 10 0.48. I get 0.99832. Now let's go a bit further. Suppose I ask probability that X is more than 5. Probability that X is more than 5. Now, we happen to have that here. More than 5 means what? Start from 6, right? More than 5 is start from 6. Now, the thing is, I don't have probability that compute greater than or greater equals than. I have the feature on my calculator to compute the probability up to a certain number. Okay, now I know the total probability should be 1. So for me to compute that, for me to compute this greater than 5, I will do the compute the complement. That will be 1 minus probability that X at most greater than 5 means start from 6. Okay, now the complement means up to 5. Okay, which is equals to 1 minus binom CDF 10 0.45, which we happen to have done in part D. That's 1 minus 0.83376, which is 0.16624. Okay, now I strongly suggest you to imagine the boxes I did earlier. So let's say just for other fun, suppose I ask find the probability that x is greater equals to 8. Greater equals to 8 means from all those possible outcomes, I will take the outcomes 8, 9, 10. Okay, that's what I want. However, again, my calculator cannot compute probability from x greater than for binomial distribution. Then I will do the complement. This will be 1 minus probability x up to what? Now, you look at this. The complement of 8 or more is 7 or less. Okay, so probability 1 minus probability x is at most 7. Now then from here we use calculator 1 minus Binomcdf 10 0.47. That is equal to 1 minus 0.98771, which is 0.01229. Okay, now that's the theory and notation and calculator for this binomial distribution. I give you the notation, learn to write it this way. It really helps us to simplify our notation though. Learn to write it this way. Okay, and then I already taught you the calculator use and the notation. Now, let's try the actual problems, the actual word problems. There are a lot of actual word problems possible. Would anybody like to tell me what's your major? Okay, let's see. Philosophy, nursing, econ, art. Let me use nursing. Nursing major. Okay, let's see. Here's the thing. I actually have that in mind though. The probability that someone is asymptomatic of COVID-19. A lot of people say, some people say it's 1/4, somebody say 75%. I prefer to say, use the number we have from China, because they have a lot number, earlier number there, is 86%. Okay, that's the result from a lot larger number. We are talking about like around 50,000 to 80,000. I'm not sure precisely. I don't remember on the top of my head. But they found that approximately 86% of people tested positive of COVID actually not showing any symptoms. That's the reason I strongly support our governments to tell us to stay home, because you don't even know if you are actually carrier, but you may end up spreading the disease. Okay, now if you want to spread your disease, then do it at home. Okay, I know this sounds really bad, but if you, I joke with my friend this way. It's like, how do we know, we, especially because we are younger, right? We are like around 40 years old. Some people with 40 years old have symptoms, don't get me wrong. However, people who are not showing any symptoms tend to be on the younger age, like less than 40, even less than 20. Now, how do you know that you are having COVID or not without doing the testing provided by the government or by hospital? Easy. Hug your grandparents. If within 2 weeks your grandparents sick, then you have it. Okay, now I don't think you want to do that, right? Okay, please don't. Please don't. So regardless you have it or not, don't do that. Do social distance and physical distancing. Okay, let's come back. Suppose the probability someone is asymptomatic of COVID-19 is 86%, and there are, let's say, 10 students attending a class. For now, let me change it to 20. For now, let's change it to 20. Okay, and we are interested in find the probability that let's say 15 students are COVID positive. Well, because they are attending the class, then they are not showing any symptoms, right? Okay, because if they show symptoms, they usually don't show up. Okay, I don't think you want to show up if you have some symptoms. People with COVID-19, if you show symptoms, it's usually progress really fast and get really worse a lot really fast. Okay, now, so if you don't have any symptoms and I say, hey, you know what, let's have a class. Then if you show up, very likely you don't have any symptoms, even if you are tested positive. Okay, but suppose you don't know if you are positive or not. Okay, all we know is that you are without symptoms. Okay, then what is the probability that 15 students actually tested positive? Let's start with some notation. You don't need to show this notation in your test, but I will write it here for the purpose of clarity. Let X be the number of students COVID positive. Okay, so if you are asked, if you don't know you have it, but you don't have any symptoms, the probability that you actually have it is 86%. Now, you have 20 students not showing any symptoms. We don't know which and how many actually COVID positive. Okay, then this X will be binomially distributed. How many trials? There are 20 students that represent our number of trials. Okay, the probability that they are COVID positive is 0.86. Okay, then what is the probability that X equals to 15? This is actually a bad example though. Not really appropriate, not really appropriate. Okay. So to be more precise, of 20 students, of people who is COVID positive, 86% of them not showing any symptoms. Okay, but let's suppose that you have 20 students, 86% not showing any symptoms, and what is the probability that 15 of them not showing any symptoms? And that would be Binomcdf 20, 0.86, 15. Binomcdf 20.86, 15. I get 0.08681. Thank you. Okay. My illustration here is actually not correct. Let me change the wording a little bit. So there are 20 students tested positive. What is the probability that 15 students are asymptomatic? I said it wrong. Are without symptoms. And probability that 15 of them showing no symptoms is 0.08681. Now, the crucial question is, what is the probability? Find the probability that no student, actually I prefer to say all students without symptoms. All students without symptoms. So you have 20 students, okay? They are all tested positive. Okay, what is the probability that all of them show no symptoms? So probability that the number of people, the number of students not showing any symptoms is 20. It's Binomcdf 20, 0.86 point. We get 0.04897. Yeah, we do it to 5 decimal places. Okay, so 0.04897. If we round it to 3 decimal places, then that's correct, 0.049. But to 5 decimal places, 0.04897. So you see how scary it is that what's so scary that you may go into a room with 20 people tested positive, all of them tested positive, but none of them show anything. Okay, so imagine you have a room full of people tested positive, none of them show any symptoms, and very likely they themselves don't know that they are tested positive, but once one person 70 years old or 80 years old get into this room, then within 2 weeks, this person very likely die. This old guy very likely die. Why? Get contracted by 20 people. You see what I mean? So the probability is still almost 5% though. And that's not rare, you know. And if you have one guy like to socialize so much and just keep on showing up everywhere, then you see this person will get contracted. Okay, that's why we do this social distance. Now, I usually don't like to express my support for any government's rule, government's policy. Though, I mean, in this way, even if I support it, I usually don't say anything. You know what I mean? But so this is one example. Let's do another example. Let's see. Somebody say that, Thomas, I'm from sociology. Well, sociology, let's do this. Sociology, political science. I think we can say the following. Suppose, for example, I don't know example number what, and we say 75, maybe 76%, just make it a bit uglier. 76% of US population disagree with the way our president handle COVID-19. This pandemic. Okay. Again, I believe I already said the disclaimer. Whatever example I use in this class is not supposed to be interpreted as my support or against certain policies, certain people, or against the government or support the government. No. It's just, we just see this from a statistic point of view. Okay, so even the one I said earlier that I support our government with this social distancing, if you disagree, don't worry about it, nothing against you. Okay, you have the right to your own opinion. Okay, and even if I disagree with you, I will do everything in my power to protect that right. The right of being different from me, myself, and your right to be different from everybody else. Now, that's democracy, by the way. Okay, now let's say 76% of US population disagree with the way our president handles COVID-19 pandemic. Then, suppose we randomly survey some students. Can you suggest to me how many students? You make up the number. 23 students. Okay, suppose we, oh, you know what? You gave me two numbers. Okay, suppose we randomly survey 69 students. Find the probability that more than, is it 23, the other number? Yeah, more than 23 students disagree with the way our president handles COVID-19. So let X be the number of students disagree with the way our president handled COVID-19, then this X will be, well, either you agree or disagree, right? So binomially distributed, number of trials, 69, probability of success, that probability that a student disagree is 0.76. Okay, now then, the question here, find the probability that more than 23 students actually disagree. More than 23 means, if we look at the possible outcomes, more than 23 means starting from 24 and on. Right? Okay, now the complement of more than 23, the complement of more than 23 is at most 23. So I strongly suggest you to draw this diagram here. More than 23 starts from 24. Okay, so the complement will be up to 23. So 1 minus probability that X is less than equals to 23. Then I use I write the calculator notation first. 1 minus binom CDF 69 0.76 23. Oh wow, I get very, very small now. You chose the number. Okay, I get 6.74019. But at the end, you see e to the negative 14. That's the same to say times 10 to the negative 14. Now, this number, by the way, this number, if I write it into decimal, that's the same to 0.0000, a lot of zeros, and then 674019, where the 6 here is at the 14th decimal place. This 14th decimal place is here. Okay, so that's very, 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 very small. So when we subtract this, we will get, don't write this down, But when I subtract this and I write everything, I should get 0.999, so many nines. And then 326981. These 3 here will be at the 14th decimal place. Okay, So if I write the first 5 decimal places, that will be 0.99999. However, the 6th decimal place is still 9, right? Therefore, if I do rounding to the nearest 5 decimal places, that will be basically 1. Yeah, because the number I shade in yellow is so small such that when I subtract from 1, it will be just very slightly less than 1. If I round to 5 decimal places, that's basically 1. So, so if somebody asks you to bet, to gamble, okay, Thomas, there are 69 students in a classroom. We know that 76% of our population, so including these students here, disagree with the way our president handled COVID-19. Okay, what is the probability that more than 23 of these students, of these 69 students, actually disagree with the president? Then I will say 100% sure that it is more than 23 students. Okay, we are nearly 100% sure. It's so close to 100% because the probability here is 1. Okay, now that's for this binomial distribution. Let me continue right away to 5.4. I will put them together in the same section. It's just a little continuation. 5.3, 5.4. So suppose if we have x is binomially distributed with parameters n, p. Every statistic and probability textbook that goes into try to prepare you for higher level always teach you this notation. Even if you go to Wikipedia, okay? Even if you go to Wikipedia, you type binomial distribution, then in the explanation they will use this notation too. So I'm not just some people, some minority of people, teachers that using this notation. No, those teachers who teach binomial distribution will use this notation. Okay, yeah. And distribution, the notation actually help us to summarize a lot of things into a very short sentence. Now, in 5.4, we are asked what is the mean of such binomial distribution. The formula is NP. N times P, while the variance is N times P times Q, where the Q is 1 minus P. Okay. Now, suppose I continue from our previous question. If I continue from our previous question, X is binomially distributed with N equals to 69 and probability of success, in this case, probability that the student disagree is 76%. Then, if you have 69 students, how many of them we expect? How many of them we expect to disagree with the way our president handled the pandemic? And that will be N times P, which is in this case 69 times 0.76. 69 times 0.76. I get 52.44. Don't need to do rounding. don't need to do rounding. But Thomas, the number of people who agree or disagree should not be 52.44. I know, but when it comes to average, it is okay to have such decimal. Okay, so the expected value is 52.4. So if assuming that the hypothesis 76% is true, assuming that 76% proportion of our population disagree with the president is 76%, then given we have 69 people in the room, for example, then the number of people disagree with the president should be not too far, if not equal to, not too far from 52 people, 52.44. Okay, now the thing is, what is the variance? Then the variance will be NPQ, which is 69 times 0.76 times 0.24. Now, where do you get this 0.24, Thomas? That 0.24 comes from 1 minus P, 1 minus 0.76. Which, when we compute, we get 12.5856. Now, what is the reason we want to find the mean and standard deviation, the variance? Well, from the variance, then we can go on finding the standard deviation, right? Which is the square root of that 12.5856. I get 3.54762. Okay, now then what is the reason we find the standard deviation? One of the reason is once you have the mean and standard deviation, one of the big reason, at least at this point, is to find what we call usual interval. Now the usual interval, as we have learned before in your test 1 number 9, as I remember, that is mu minus twice standard deviation, mu plus twice standard deviation. So the lower fence will be 52.44 minus 2 times 12.5856. Oh, I'm sorry. No. I copied wrong. 2 times the standard deviation. 2 times the standard deviation is 3.54762. .44 minus that answer 2 times standard deviation, I get 45.34476, while the upper fence, that's 52.44 minus 2 times 3.54762. Actually plus, not minus. So that should be 52.44 plus 2 times 3.54762. I get 59.53524. So the usual interval will be from 45.34476 to 59.53524. So suppose you tell me there are 69 students in the class, and we know 76% of our population disagree with the president. Then how many people, how many students of these 69 students should disagree? Then I say, well, between 46, it's more than 45 something, right? Approximately between 46 students up to 59 students. Okay, so if it is less than 40, less than 46 or more than 59 students, I will start questioning either that 76% is true, or are these students already brainwashed, or these students are basically coming from different type of population. Okay, yeah. Of course, if you try to interview students who happens to be Republican, for example, who tends to support the president, then the 76% does not apply anymore, right? Okay. Now, of course, if you also do the interview on right in front of a democratic office, for example, and of course, most people going to that office tend to be against the president, tend to be in whatever he says. Okay, yeah. So anyway, that's the way we apply our. That's the way we apply this the mean and the variance here. Right now it's 12:23. Let me get a short break. One or 2 minutes. So let's continue. Oh, I'm sorry, the recording is going. I forgot to stop it. So this will be 4.7 times 60. I wonder what's that. 47 times 6, 240, 282 per hour. So the probability that x is less than 100 in 1 hour will be probability that x is less than equals to 99 in 1 hour. That is equals to Poisson CDF 282,99. What is this? I get, I'm sorry, I'm surprised myself. 2.09002 e to the negative 36 basically times 10 to the negative 36. That's so small. That's very, very small. That's approximately 0. So with this kind of like, with this kind of number of customers going to this store, you can imagine Costco in regular time, not during this time. In regular time, if the average of number of customers going to the store is 4.7 per minute, then it's actually basically unbelievable. It will be unbelievable if less than 100 going to that store in 1 hour. Like if it actually happened, then something bad must be happening, or something, I should say, something must be happening. That's not normal situation. The manager is supposed to act right away. Okay. Is there anything wrong with the way we do the surface? Or is there anything wrong with the street, just in case something blocking? Okay, so on and so forth. Now, one of the use of this Poisson distribution, beside number of arrivals, you can also see, for example, number of errors. You know what? Let me go to Wikipedia and show you the cases where Poisson distributed is being applied. So I go to Wikipedia. I type Poisson distribution, I Google it, and then I go to Wikipedia. Yeah. From here, do you see this Wikipedia, everybody? Okay, I'm just afraid that I'm on different page. Okay, now then, why we call that Poisson distribution? Well, because it's named after a French mathematician. Okay, because it's French, then we don't read that as Poisson, it's Poisson. Very similar with the nasal voice we use to read croissant, the type of French bread. Okay, croissant, this is Poisson. Okay, that's what the graph look like when we apply Poisson distribution in some particular cases. But I am interested in, for example, see, what is Poisson distribution? It's popular for modeling number of times an event occur in an interval of time or space. This is the formula, but we will not use that because we already use calculator. Okay, the lambda, the average, is expected value, which is the same to the variance. So if you have a situation where the expected value and the variance are very close to each other, then we suspect that the distribution, the underlying distribution, could be Poisson distribution. Now, the examples where this being used, the number of meteorites greater than 1 meter diameter strike Earth in a year, the number of patients arriving in emergency room between 10 to 11 o'clock at night, the number of laser photons hitting a detector in a particular interval or area. Okay, if you read our book, from my example, you see we use this Poisson distribution for the number of arrivals in a store. You can also use that for the number of arrivals in a bank, let's say. Okay, so you know you don't want to go to a bank during lunchtime. Okay, preferably before or after. Okay, if you read the book and in other resource, this is also the model we use to predict the number of earthquakes happening. Okay, and also on our textbook, or I think I saw it somewhere else, that we use Poisson distribution also to predict the number of potholes on freeway. Okay, now on our screen here, we see an example on a particular river. Overflow floods occur once every 100 years on average. So you have a river, the flooding happens once in 100 years. Okay, so then you see the average is 100 years, 1 in 100 years. Okay, now how about the number of goals? The number of goals in a World Cup match will be what? Okay, on average is 2.5 per match. That's still Poisson distribution. Okay, that's for this Poisson distribution. Let me see if we can find a good question from internet. Poisson distribution example. Now you know how I get my problems. I don't want to write my own problem, because then later on a student may say, Thomas, I don't understand your English, right? Okay, so let's do this one. Let's do this one. Lecture 5, Poisson distribution. And this is, if you read this, let me ask you this. If you read this, the URL, can you tell where is it from? Okay, nobody know. You cannot tell. Oh yeah, I see somebody say. Yeah, it's from UK. That's right. Can you be more specific? That's from Oxford, not Oxnard. No, that's from Oxford University. Okay, can you tell what major? Statistic major. That's right. So we apply this. So see, what I teach you here is not only taught at ELAC College. It is actually taught at Oxford, a university that everybody respects. Okay. And of course, the reason I teach you what they teach there, so that the course you take here at ELAC College is transferable to Oxford, right? Okay. Even though it's it doesn't have to be in sense of transferable. So what I want is when you graduate, you can do what they do. Okay. Now let's see. the experimental situation occur, many experimental situations occur in which you observe counts of event within a set of unit time, area, volume, length, for example, those. Now, let's see. I will try to get an example. How about this one here? And I think I should enlarge that. Do you see the enlarged version? Do you see the enlarged version? Okay, good. Now then, we see births in a hospital occur randomly at the rate of 1.8 births per hour. What is the probability of observing 4 births in a given hour at a hospital? And the first thing they do is define the random variable x. Let x be number of births given hour. Okay, and then you see this notation here. They use x Poisson 1.8. Okay, this is the old notation. Okay, instead of PO, we tend to write Poisson right now, but don't worry too much about that. If you write PO parentheses 1.8, I will accept that, even though at the same time I think you may be older than usual. No, that's joke. Okay, now then, what is the probability? What is the probability that there will be 4 birds given in 1 hour? They use this formula. Apparently, they rounded to 4 decimal places. Can you do it with your calculator? Please do it with your calculator and tell me what's the answer in 5 decimal places. The average is 1.8 per hour, and we want to compute the probability of getting 4 birds in 1 hour. Now, can you tell me your answer in 5 decimal places?
0.07231.
Oh, no. 230.
Yes, 0.
Yeah, 230, because the next number is less than 5, right? Okay, so the answer is in 5 decimal places, that's 0.07230. Let's see the next page in case they have a follow-up question. Oops, too much, my bad. This is what we have earlier. Why? Hey, what did I do? Because I want to follow you. Okay, how about the next follow-up question? What about the probability of observing more than or equal to, or equal to 2 birds in the given hour? 2 birds in a given hour. Let me copy this and bring us back to our paper. Suppose we have that. You are now on my note, right? Supposed to be. And the lambda equals to 1.8 birds per hour. Now, this is the way they compute it. This is the way they compute it. That's because they don't use TI 83 or 84. Okay, so they are more into theoretical approach. By the way, that's the way I taught that I taught my class in the past. Okay. But right now, because we have calculator, then that's the probability that 2 or more birds That's equal to 1 minus 2 or more birds. Means it starts from 2, go to infinity. Now then, the complement is up to 1. The complement is up to 1. So probability x less than equals to 1. That's 1 minus Poisson CDF 1.81. It's 1 minus Poisson CDF 1.8, 1. I get 0.46284. If I subtract from 1, I get 0.53716. So you see that my computation is more accurate compared to what they have here. Okay, I think they already did some rounding here. They already did some rounding. So this what happened here. They have even more rounding. Okay, but even if we round to 3 decimal places, we will get the same answer. Now I will stop the lecture here.